It's have 30 minutes pause, and then after that we will do a remote demo from Germany to show you the whole live demo from Germany. I think it's still the same link. The same thing will be on Thursday. So first I will give the presentation. After 1 hour presentation, half an hour pause, and then we will have a live remote demo from Germany to show you the MinFlux on Thursday. So today MIRAVA talk and the demo, Thursday the same thing on the MinFlux. Now, first I switch off my video so we can focus on the screen. So today I'm going to talk about Abberior super resolution nanoscopy. I'm going to show you the STED part, which is based on our large MIRAVA platform. So I study neuroscience. I use the structure of the synapse to start. So this is the physical size of the synapse. As you know, for example, the synaptic vesicle, the diameter is typically 40 nanometer. This structure somehow cannot be resolved by conventional confocal microscopy or other optical microscopy, because we know from the confocal microscopy laterally the resolution in the XY is around 200 nanometer. However, with STED super resolution, the resolution in the XY is 20 nanometer, and with our latest technology, MinFlux, the resolution is around 2 nanometer. We can do a lot of interesting research. The resolution improvement has dramatic influence on the scientific data quality, as you can see here. If we take the imagery from the confocal, it's misleading. You will see colocalization or translocation of the proteins, right? And from the STED image, it's so clear. From the raw data, optical raw data, you see they are apart from each other. So the magenta color is in the pre-synaptic compartment, and the green color is in the post-synaptic compartment. So it's not misleading. So talking about super resolution, we have to mention Stefan W. He is the first one in the world who has the super resolution optical microscope concept. And he actually invented the STED, he invented the MinFlux, he is the founder of our company, Abberior Instruments. And I also would like to emphasize, from our STED system, we only show you the absolute raw data on the screen. What does absolute raw data mean from our system? It's photo counts per pixel directly from the detector, as you see here from the screen. There's no post-processing, no calculation, no background subtraction, no smoothing of the image. It's the pure photo counts per pixel directly from the detector. Therefore, in our MIRAVA system, there's no gain this concept as you learned from other confocal microscopy. There's no average. So since everything is physically presented to you, it's the direct physical number of all the photons. And in Stefan W's lab and in our company, we use nuclear pore complex as the main benchmark. So it is a very complicated structure and very important. As you see here, it sits across the nuclear membrane. There are a lot of proteins, right? And the diameter is below 200 nanometer. Therefore, you cannot resolve the structure by an optical microscopy. So all the studies were done on by electron microscopy previously. And then from the electron microscopy data, we see there are 8 subunits in XY symmetrically, and in the Z, it's asymmetric. Right? If we want to see this structure by an optical microscopy, it looks like this. It's blurred out in the conventional microscopy. This is the official flight from Nobel Prize 2014 chemistry. They use Abberior Instruments, actually our STED, to image the nuclear pore complex. As you can see here, the STED resolution is 10 times better than the confocal. You can resolve the 8 subunits, and while the green is in the center is the central protein. In that year, the Nobel Prize was awarded to 2 technologies. One is STED. STED is based on a scanning confocal microscopy. Another one is based on single molecule localization, PALM or STORM. It is a wide field camera-based system. Normally, you need a TIRF microscopy, total internal reflection microscopy. These 2 technologies in 2014 can reach the resolution in the XY at 20 nanometer scale. So that's in 2014. And then in 2017, from us, we launched the MinFlux. As you can see here, we use nuclear pore complex 19-6 protein as an example. So from the electron microscopy data in the middle, we know there are 32 copies of that molecule. In each unit, there are 8 subunits, right? In each subunit, there are 4 copies of this protein. 2 are outside the membrane, 2 are inside the membrane. And then you can measure the distance between subunits and diameter of the nuclear pore complex. Now, with the MinFlux, which is an optical microscopy, we can get the same data. You see the localization of that protein, nuclear pore complex 19-6. And then you measure the same data as electron microscopy already showed you. However, what more is from MinFlux, you can do the sample preparation in fixed cells, in live cells, and then later we launched 3D, 2-color, and even we can do the single molecule tracking. The resolution in the 2D, it comes down to 1 or 2 nanometer. So now you see here, instead, the resolution is 10 times better than the confocal. And MinFlux is actually 100 times better than the confocal. It's really single molecule imaging. And sorry, this is a review paper published in 2017. It showed all the PSF in all kinds of optical microscopy, super resolution or high resolution. What does PSF mean? It's point spread function. It shows you the smallest dot size and shape in each kind of technology. So the up panel, the scale bar is 200 nanometer. The confocal, we set the confocal as a reference. XY is 200 nanometer. In the Z, it's elongated. It's 500 nanometer. That's confocal. Somehow, confocal method is pure optic. All the other methods with the stripes, like deconvolution, area scan, 2D sim, 3D sim, lattice sheets, you need post-processing, algorithm calculation to boost the resolution. 2-fold is better than the confocal. The lower panel, the scale bar is 50 nanometer. As you can see here, STED is actually a pure optical method, physical method. From our STED, the XY resolution can reach 20 nanometer. And if we want to do 3D STED, we can reach the resolution isotropically 60 nanometer in XYZ, isotropically. This is one Nobel Prize technology. Then we have in the middle, Palm and Storm, single molecule localization-based super resolution. Through the calculation, the XY resolution is also around 20 nanometer, and XYZ resolution is in a similar range as our isotropic step. And then we have the combination of the best from the STED and the single molecule localization. Then we have the MinFlux. Also through calculation, the localization precision is around 1 nanometer. So on this slide, it's an overview of all the super resolution methods. So there are 3 categories. The first one is structure related, either structure illumination, SIM, or structure detection, like spinning disk, array detector. We also have our own array detector. You're going to hear it in our MIRAVA. So all the structure-based method, super resolution, boost the resolution 2-fold as better if you compare to confocal. In the middle, it's single molecule localization based method like Palm and Storm. It's 10-fold as better than the confocal, and our Abberior MinFlux, it's 100-fold as better than the confocal. The third category is STED. STED is 10-fold as better than a confocal microscopy and is the only super resolution method with directly physical output and easy to use as a confocal. All the other methods, super resolution method, you need algorithm calculation, and hence it's sample structure and sample preparation dependent. So you have to be actually very careful with their post-processing because it can change the authenticity of your scientific data as you see here. So, right, we have original low resolution but very true data from Elon Musk. And from the post-processing, you can easily calculate it into an African version or an Asia version, which is actually misleading. Now, I would like to talk about the basics and principles of the diffraction barrier and the STED principle. So we know 100 years ago from Rowley, from Abbe, already the optical microscopy has a diffraction barrier. It is related to the wavelength and the numerical aperture of the lens. So the diffractive index and the angular angle of the lens. What does that mean? It means a point light, when it passes through the lens system, it will be elongated, as you can see here. The excitation beam is elongated into an elliptical sized, large American football sized this dot pattern. In the XY, it's 250, and in the Z, it's even 550 nanometer. So this is a large, actually, light dot, which is scanning your sample in a confocal microscopy. And then, for example, in this illumination volume, there are 5 molecules being excited, and every of these 5 molecules, they emit light. And every light from these 5 molecules, when passed through the optical system on the detector, they are elongated again into a large American football-sized point spread function, this dot. And obviously, they overlap to each other. And actually, this volume is even larger than the excitation volume because of the Stokes shift. That's the diffraction barrier. And if we want to do super resolution, we have to make it smaller. And instead, is a kind of method that we shape the PSF into a small volume. If you compare the STED formula to a normal confocal formula, as you can see, they are very much similar to each other. What does that mean? It means that STED microscopy is intrinsically an optical perfect confocal microscopy. Otherwise, if the optical part is not good, it contacts the resolution performance. So remember, any STED microscopy is an optical perfect confocal microscopy intrinsically already. Then the super resolution part, is coming from the dye. That's why it's a Nobel Prize in chemistry. If the dye can handle a lot of STED power, it can improve the resolution. That's the STED effect I'm going to explain you in this slide. On the right side on the screen now, you see the true imaging of the excitation Gaussian beam at the back focal plane of an objective. So the diameter, the smallest diameter, is around 200 nanometer, right? That's the physical barrier, and you cannot make the beam even smaller. So actually, it's a large pattern, and all the fluorophores are excited. What does that mean? It means the electrons get the energy and jump to the higher energy level and stay there. There's some vibration, and it jumps back to the ground state and emit light. That's how the fluorescence is generated, right? So in the STED, when the electron is excited to the high energy level and stay there, there's a special term called FLIM, fluorescence lifetime, right? Exactly, it's that time. In the fluorescence lifetime, if you introduce the STED beam in a donut shape overlapping to the confocal excitation beam, what would happen? In the overlapped area, there's STED effect. So the STED beam will quench the excited electron, and then it will be de-excited. And then the energy will be used to generate a second STED photon. Okay? Without STED beam, the energy will be used to generate the signal spectrum photon. With STED beam, the energy will be used to generate a second STED photon. So actually, the process here is the same as how the laser is generated. Light amplification by stimulated emission of radiation. STED is stimulated emission depletion, right? So So in the overlapped area, you have more and more stared photons. Then it is easy to filter the stared wavelengths by a very good filter in front of the detector, and then only allowing the middle part, the donut center, where there's no stared beam. Then you have the normal confocal excitation and emission, and you have the signal spectrum of that waveform. That's the stared. So it means the stared, the timing is very important in the stared. The stared beam must arrive in the film time. If it arrives earlier, there's no excitation yet. If it arrives later, there's already emission. So in our system, we are very accurately controlled this timing by all pulsed metric. You will hear it later. Then let's see the stared intensity and the resolution. What's the relationship? In the confocal system, it's a Gaussian beam. That's the smallest dot size, and the same as effective spot size. You can do nothing. If now the stared beam is deployed in a donut shape and overlapped, if we draw a cross section, so you see actually the red curve is the energy distribution of the stared beam. It overlapped to the excitation beam, which is actually green at the back. The overlapped area is dark on the detector. There's stared effect, as I explained in the previous slide. Only in the donut center, there's no stared laser. You have the normal excitation and the emission. The combined effective spot size is smaller. Then if you increase the stared power more and more, the center part is confined less and less. The resolution is improved further and further. Therefore, now you see that dye actually is very important in stared application. That's why we have actually two companies. One is called Abberior Instruments. Another one is called Abberior Dye and Labeling. And then if you can choose a very good dye, the dye can handle a lot of stared power, and then you can reach the better resolution. And then the dye can handle a lot of stared power, means the dye is very stable. Actually, you can use the dye in any other kinds of microscopy, in confocal, in spinning disk, in time-lapse, in volume 3D stack. It won't bleach. So we have very good dyes. Now we do a test. We use 20 nanometer beads, physical size, optical raw data. Okay, we only show optical raw data. In confocal, it's misleading. It's 221 nanometer. If we have stared, okay, the resolution starts to improve. Now it's 132. If we increase the stared laser power, now the center part is confined smaller. Now we reach 84 nanometer, more and more 52 nanometer to the maximum the dye can handle. It's always around 20 nanometer. So actually, you see, our stared is actually a resolution tunable system. You switch off the stared beam, it's the optical perfect confocal system. You switch the stared beam to the maximum the dye can handle, you get the best resolution. Normally, you do that on a fixed sample. And then in between, you can compromise the phototoxicity and the resolution for lifetime imaging, live cell imaging, and the Z-stack volume imaging, as you wish. This is tested by biological sample. It's nuclear pore complex, two colors in the center part and the ring part, and in the same view. If you switch off the stared beam, it's the confocal on the right side. Look at the scale bar, it's 500 nanometers. So confocal, actually the resolution is 200 nanometer. Once you zoom in, it's blown out. Once you switch on the stared beam and continuously increase the beam power, and the resolution will continuously improve till the moment the dye cannot handle, then it's bleached. So from our company, there are 3 microscopes. There are 2 different type of their technology. One is stared, one is main flux. Instead, we have 2 kinds of the system. The entry level actually is called Steadicon. Now we have the second generation. It's stared and confocal. It's a perfect optical confocal system. The second generation will have the film fluorescence lifetime imaging capability integrated. At any time, it's 2D optical raw stat resolution, 30 to 40 nanometer, without any post-processing. Optical raw data, 30 to 40 nanometer. Anytime you test with the beads, it's like that. In the middle part, it's the MIRAVA. It's a combination of all the modules from us. It can do confocal imaging, 3D stat, matrix array detector, and we have 2D mean flux module. The 2D optical stat resolution is 20 to 30 nanometer. 3D isotropic optical stat resolution, 60 to 80 nanometer. And the 2D mean flux localization precision, it's 3 to 5 nanometer. Then the last, we have the giant big mean flux. Then we can do 2D mean flux imaging. The precision is 1 to 3 nanometer. 3D mean flux imaging, it's 3 to 5 nanometer. And then we can do single molecule tracking in live cell, 100 microsecond per data point. So it's ultra fast. So today we focus on the stat part. I will show you a lot of application data from the Staticon, then we migrate into the MIRAVA. So as I said, a scientific instrument, it's very important to show the authenticity of the science, right? Now, if we are going to imaging central, as you can see here, right? From the biology, we know central is the microtubule organizing center, then gamma tubule. There should be 9 microtubule sets in the central normally. If you want to image in the central with a conventional confocal microscopy, as you can see here on the screen, it's the smallest dot, right? You read the scale bar full with half maximum, it's around 250. It's the smallest dot, and you cannot see any structure because that's the smallest dot a confocal system can produce you. With our Staticon, even our Staticon, now you can see optical raw data, 9 microtubule sets clearly. As I said, we only show optical raw data. Here's another example. Here's this customer finds some new proteins in this creature. And in the confocal, it's just like traffic light. Instead, you can even see, okay, they are at the outside of the membrane, and you can count how many machineries are there. And now this is an interesting example. The customer would like to study 2 new proteins in the focal adhesion, their interactions. In confocal, there's strong co-localization, right? And actually, she wasted 6 months to prove the misleading information from the confocal. There's no interaction at all, proved by all the other methods. Then she checked with our stat, and obviously from our stat, you see there's no co-localization at all from these 2 proteins. Actually, she regretted a lot. If she can imaging with the stat, this will save her a lot of time to prove misleading information from the confocal. Here, I have another interesting data. Another customer actually knows that there's strong interaction of the 2 proteins, but he still got the same image as you see here now on the screen. On the right side, there's no interaction. Then later, we find out the interaction of his proteins happened at the N-terminal of the protein. The antibody he used is against C-terminal of the protein. While our system, the resolution is so high, where you are going to label the protein will influence the data quality. The interaction happened at the N-terminal, while the labeling is at the C-terminal. They're apart from each other. Obviously, you see nothing, right? So here's another example, exactly shows you this concept. What the customer would like to see is the chromosome architecture during the duplication. There are 2 chromosomes, right? They're separated and the chromatin is duplicated. So now you see here, if we stain the scaffold protein, REC8, now you see 2 lines, they're outside. If we stain the C-terminal of ZYP1 protein, you see 2 lines beneath the REC8. If you stain the N-terminal of the 𝐌𝐈𝐑𝐀𝐕𝐀 protein, you see one line in the middle. You see the labeling position, it's different, then you got different result. In C-terminal labeling, you see two lines. N-terminal, you see one line in the middle. Based on this information, you can draw the diagram. The N-terminal is organized in the center, while the C-terminal, they're pointing to the side beneath the REC8 scaffold protein. And you can measure the distance, as you can see here, 213 nanometer. And our Staticon is 30 to 40 nanometer, so we can easily resolve this structure. On the right side is published data from France in PNAS. On the left side is another customer doing the same thing. In China, they tested in the rice, in the plant cells. Actually, it's the same in mouse cells. And on the lower left, it's the published electron microscopy data. It's the analog protein, same as you see in the previous slide. There's central protein in the middle, central element, and then there are lateral element, which is actually the C-terminal of the SYCP1 protein at the side. And you can measure the distance. Now in mouse, it's 100 nanometer. So still we can resolve that. Because our resolution from the Staticon is 30 to 40, we can resolve it. As you can see, the confocal, everything is blurred out. You see no details. While in the STAD, you see the scaffold protein in the magenta and the N-terminal in the middle. Now, here's again a very classical example. It's a clathrin-mediated endocytosis of a vesicle. From the textbook, from EM data, we know clathrin, it's a kind of coating protein. It holds a vesicle, right? The vesicle is inside, clathrin is outside. If you imagine clathrin in the confocal, as you can see here, it's a solid dot. It's misleading. It will trigger you to think, okay, maybe clathrin translocated into the vesicle. No, it's misleading. If you check with our Staticon, now you see the ring structure, right? And that's the truth, right? Because clathrin, it's a kind of coating protein. It holds the vesicle. It's at the outside. It will never enter the vesicle. Even the microtubule is much better resolved, while the resolution improves. And then our STAT can do a lot of live cell images. So you will hear the STAT is a very phototoxic. You cannot perform any live cells. No, it's not true. If the instrument is very well designed and manufactured with a lot of nice technology, it can do a lot of live cell imaging. As you can see here, we can imagine the live mitochondria crystal, even two colors. We can imagine every crystal of the mitochondria. The distance between mitochondrial crystal is 20 to 50 nanometer. So from our system, we can resolve each one of them. If you are going to imagine this in a confocal or in a spinning disk or in a SIM, you only see 2 or 3 thick stripes because of the limit of the resolution. While on our STAD, even the Staticon, you can see every crystal of the mitochondria lively. Then this is self-explaining that the transcription factor statistics based on a STAD imaging, it's much more accurate than a confocal, right? Here's another example. Exosome statistics in the Drosophila brain. On the left side, it's confocal imaging. Right side, it's STAD imaging, optical raw data. Now on the STAD imaging, you see the magenta, it's the exosome. You can clearly see where they are and how many of them. On the confocal, if you want to do the statistics, it's a kind of waste of time, right? Because it's not true. Then it's the same story. Then this is actually on the left side, it's the virus accumulation on the nucleus. So the customer find in some pathological condition, he saw this accumulation of those virus particles in the confocal. Without our STAT, he has to evaluate this big dot in the electron microscopy to see whether these are the aggregation or they are fusion, because the process they are different. Now, easily with our Steadicon even, you can see all the particles. Actually, they just aggregated to the same side, but there's no fusion. On the right side, it's the 𝐏𝐈𝐑𝐀𝐕𝐀 intermediate compartment in a tissue. The same thing from the optical raw data. You can see in a confocal, the structures cannot be resolved. It's a big dot. And in our STED, you can see the particles, and you can count how many of them. If you do time lapse, you can see how they are accumulated to that site. And then, since we are super resolution imaging, any questions? Okay, just raise your hand or just speak out if any questions. Okay, and then people think, okay, that's super resolution. You can only do a small region of interest, but actually it's not true. From our system, we can do a tiling of a large region of interest for the super resolution imaging. This is the tear of a sperm, the complete tear. The scale bar is 2 micrometer, and we can do the 2-color 2D super resolution of the complete tear of a sperm. The green is a microtubule in the center. The red is actually a new protein they found. And in confocal, they just merge to each other. And actually in STED, you see clearly they are actually not to each other. Actually, the red molecule, it's outside of the microtubules. So Steadicon is a very friendly system. It can be attached to any size like Olympus, Nikon, inverted, or upright microscopy. To turn that simple microscopy into an optical perfect confocal and a 2D 30 to 40 STED microscopy. You can also attach the Steadicon to any existing high-end system, like here to the Olympus confocal microscopy, spinning disk, or SIM, or our customer, he used a competitive study and was very unsatisfied and purchased our Steadicon attached to another site. So in the Steadicon, you see, it can actually outperform any confocal microscopy in the world because there are several very important techniques we applied in the Steadicon. First concept is all-time matching, all-pulse time matching. Second is we use APD detector. Third is we have very advanced scan mirrors. All-time matching, as I told you before, the STED effect is tightly conjugated to the flint time of that dye. Therefore, in our system, we use excitation pulse, and then all the fluorophores, they are excited. During the fluorophores lifetime, we shoot the STED beam in a pulsed way. Therefore, you can control them. Then the overlapped area outside in the donut, they are de-excited. And in the middle part, after 1 or 2 nanoseconds, it starts to emit light. Only till that moment, we open the detection gate. So we control the timing very accurately to that fluorophore. It's all pulse matched timing. We are the only one who's doing that. And only those time domain film companies can do all pulse matching timing at the same level as we do. Others cannot do this. Even though they are pulsed, they are not matched to each other. Therefore, after several rounds, there are only several pulses they start to match, then mismatch again. So the efficiency is very low. Or even worse, you just use continuous wave STED beam. As you can see here, the effective time of the STED is only within this 1 or 2 nanoseconds. The continuous wave STED is shining to a sample all the time, while in the effective STED time, a continuous wave STED, the photon intensity is much less compared to a pulsed STED. Therefore, it's not efficient. It's not efficient in the STED effective time, and it's bleeding your sample all the time outside this time window. Obviously, you cannot achieve very good STED quality. Second, a detector. 100% commercial confocal system or two-photon system, they use PMT, they use GASPR, they use hybrid detector, which is actually a modified GASPR detector as the detector. All these detectors, they have the same vendor, Hamamatsu, Japan. We use true single photon counting APD detector, avalanche photon detectors. We use this detector in all our system. The same detector has been used in our MinFlux even. So you see the detection efficiency is much better than any commercial confocal system. Then we have a very good quad scanner. All the commercial system, you have two mirrors, X and Y, and then we have 4. All the commercial confocal system, the mirror scanning resolution is 4K normally, maximum 8K. We have 16K. We have 4 mirrors 16K to provide the perfect optical quality of a STED. That's our scanner in our system. So all these 3, they are in the Steadicon system. Now we come to the MIRAVA polyscopy. The MIRAVA, it's a system, all-in-one system, imaging across all scales from millimeters down to 3.2 nanometer. What you see here on the screen is a retina. It's a tissue imaging, retina synapse. So it's a millimeter scale. If you choose a region of interest, you can do the confocal, the resolution in the XY, down to 200 nanometer. If you use matrix array detector from us, through the post-processing, it can boost the resolution down to 70 nanometer. If you use optical STED, XY resolution is 20 nanometer. As you can see here, the synapse structure is now very clear. Then, furthermore, you can do single color 2D MinFlux imaging. The localization precision is 3.2 nanometer. So actually, with one system, you can imagine all the resolution scales, right? From the tissue to the single molecule. So obviously in MIRAVA, we have all pulse matching timing, we have APD detector, we have quad scanner. It has much more advanced module. For example, first, we boost the STED laser power to 2.7 watt, the highest in the world. The Steadicon is only half. All the competitors, they're at the half level. As I told you before, the STED laser beam, the power is directly conjugated to the resolution, right? Now we have in the STED 2.7 watt. You can also think all the optical components in our system, in MIRAVA, they can handle 2.7 watt. What does that mean? It means they are cutting edge quality. They are very good. Otherwise, they will be burned easily. In a confocal system, the excitation laser beam, it's only like 30 milliwatt, 50 milliwatt, 100 milliwatt, or in a storm system, it's 200 milliwatt, 300 milliwatt, maximum 500 milliwatt. In our STED, it's 2.7 watt. So we use very good optical components which can handle this laser power. And now with this one, these 4, already we can boost the optical resolution in the XY to the next level. This is our actin stress fiber super resolution STED imaging. And on the right side is the electron microscopy image. A lot of people think actually our optical actin stress fiber, they think it's kind of electron microscopy if I do not tell them the truth, because all the details of the structures, they are preserved. They can be imaged with our MIRAVA level system. This is facility line. Actually, it's the predecessor of the MIRAVA. MIRAVA is even better. And then on the MIRAVA, we have a very interesting model called flex exposure. It's active protection of the photobleaching. Saved a lot of signal photos. There are several modules of this flex exposure. I'm going to tell you two of these modules. The first one is called diming, dynamic minimal illumination. What does that mean? In a conventional STED microscopy, you have the Gaussian excitation beam and the STED donut beam. They merge to each other. They are switched on all the time, scan the sample. You cannot interfere this process, right? You cannot protect the sample in an active way. In a diming, we use confocal to probe pixel by pixel. We only switch on the STED beam once there's signal in each pixel. So actually the maximal STED power, which equals the best resolution, is only switched on when there's a sample structure in the pixel. So it's a very clever way. We call it flex exposure or adaptive illumination. It's very clever. Now we see, sorry, we see an example. This is a nuclear pore complex central protein. We first imaging with confocal. Pixel by pixel, we can judge whether it's signal or it's background. Then we shoot a low dose STED beam to the red pixels in the confocal mask, only to those places, to fine-tune the mask. Now you see the blue area, they are actually background, which is misjudged in confocal resolution as signal. Actually, they are background. Okay, so we use the intermediate STED, which means low power STED, to fine-tune the confocal mask. And then in the final imaging, we switch on the highest STED power only to those red pixels in the middle picture. In this way, you saved 80% light dose to achieve the same resolution. Okay, so it is a very clever way. As you can see here, it's a nuclear pore complex central protein. In the final imaging, you can count how many of them and where are they. In the confocal, you see no details. You cannot do any quantification. And the intermediate STED imaging, actually the resolution is around a SIM or spinning disk. This is the paper published in Neuron in 2022, May. You read the title. It's high throughput single neuronal vesicle STED imaging. Co-localization of different neuron transmitter transporters on synaptic vesicles. It's 40 nanometer scale co-localization, right? Synaptic vesicle, it's 40 nanometer scale. This is not possible with confocal. The resolution is poor. This is not possible with conventional STED because of the photobleaching, because we are doing co-localization at 40 nanometer scale. This is only possible if we switch on the dynamic illumination module, adaptive illumination, to protect the sample bleaching. Therefore, it's possible to study the co-localization on 40 nanometer scale and can do a high throughput statistics. That's the Neuron paper. Another module in the flex exposure is called a mean field. So the minimal field, minimal region of interest. As you can see here, the field of view is less than 200 nanometer. What does that mean? It's just one dot. In a normal conventional confocal, you scan 512 times 512, right? You have so many dots. We only imaging one dot from that large frame. We have the STED beam just circling around that dot to boost the resolution. For example, that's a nuclear pore complex. The diameter is below the diffraction barrier, 200 nanometer. It's just one dot. Optical raw data, 8 microtubule sets. We can imaging the live HIV virus. As you can see here, 160 nanometer optical raw data with this mean field module. It's a flex exposure to protect sample bleach. We have this technique actually a long time ago. The first paper was published in Science in 2012, together with Stefan W. Hans-Georg Kreuslich, he's a virologist in Heidelberg, Germany, a very famous one, who studied the HIV virus. In 2012, we already published in Science the live imaging of the HIV virus, single virus particle. Then they have our old generation STAT system, and this system has been upgraded to a two-color 3D STAT. Now he published in Cell in 2024 how the HIV capsid cracks the nuclear pore complex. Now it's 3D, right? It's not 2D, it's 3D, how it enters the nuclear pore complex. Two-color 3D STAT imaging publication in Cell 2024. Later, with mean flux technology, he can even resolve the nano architecture of the HIV virus. Look at the scale bar, it's 100 nanometer. It is published in December 2025 on ASC Nano. So all the time, he has the cutting edge microscopy from us. All the time, he can do the leading research of the HIV virus. Now, previously, what I'm telling, they are 2D STAT. Now we want to do 3D STAT. We use adaptive optics module to do the 3D STAT. The module we used here is spatial light modulator, SLM. It's a kind of adaptive optics. We know the confocal PSF, it's like American football. If we have the 2D STAT donut, you will improve the 2D resolution, while the 3D resolution, actually, there's no improvement. It's the same as a confocal microscopy. It's like in the Steadicam. Because the 2D donut, there's no effect in the 3D, as you can see on the left side of this diagram. If you want to have the 3D STAT effect, you must have 3D STAT donut. So at the focal plane, up and lower. However, this one, then the 2D performance is poor. So if you want to have a 3D PSF of the STAT, you have to combine the 2D donut and 3D donut and make them together a perfect 3D STAT PSF to shape the confocal PSF into a small dot from the 3D point of view. The concept is easy, right? And the effect is also very good. So this is the Z stack of nuclear pore complex 153 and lamine. You can do the Z stack with confocal PSF. It looks like polar light. It's beautiful, but the resolution is poor. You can do the Z stack with 2D STAT PSF. That's the Steadicam. Now you see it's like a needle. The XY resolution is improved. The Z resolution remains the same as confocal. If you perform the Z stack with 3D STAT PSF, now XYZ isotropically, they're perfect. From the instrumentation, actually, principle it's easy. You have a 2D donut, you have a 3D STAT donut, and you merge them. However, the approach is very difficult. The stability is a big issue. Even we cannot make it so stable. Therefore, we used adaptive optics. All the adaptive optics, they're coming from the space technology. This is James Webb Space Telescope. This is the main mirror. It's a very large mirror. It consists of a lot of small mirrors. And actually, each of the mirror can be tuned to an angle to fine-tune the final imaging to compensate the distortion from different angles to improve the resolution. So we have the similar concept in our microscope. The SLN to generate the 3D stead beam. We use just one beam to generate the stead 3D donut with the SLN. As you can see here, it's just one beam. I use artificial color to separate them. Okay, it's one beam. They are not two beams merged together. It's just one beam. The artificial color just let you see it clearly. The green is the stead donut responsible for 3D, up and lower. The cyan color is the cross-section of the 2D stead donut for X, Y. And then you have the confocal excitation beam merged together to this 3D stead PSF. Then only the middle part is shaped to a perfect isotropic ball. In the middle part is scanning your sample. The resolution is improved isotropically in X, Y, and Z. So we can test with nanoruler. This nanoruler in the Z, it's apart from each other 70 nanometer. There are only a little bit molecules there. If you check with confocal, optical raw data, okay, optical raw data, confocal Z resolution, 500 nanometer. You cannot resolve these two molecules. With our 3D stead and with the protection of diamond module to, because there are only a few fluorophores there, so we use this diamond module to protect the sample bleeding. You can resolve the 3D resolution as measured here 66 nanometer, which is very close to the reality 70 nanometer. This is, for example, mitochondria from the Z section. The thickness of the mitochondria is only 300 to 500 nanometer. It is not possible to do the Z stack, right? Because one Z in confocal resolution is 500 nanometer. The physical thickness of the sample structure is 500 nanometer. There's no way to do the Z stacks sectioning. No way. It's just a one section. And then if you see confocal, it's misleading. If you see with the 3D stat, it's clear. The molecules, they're outside the mitochondria. In the confocal, it's misleading. The resolution is not good. In 3D now, you see, it's misleading. You will think the molecule, they enter the mitochondria. We can test with the nuclear pore complex. Optical raw data, right? The red is the lamine. The green is the nuclear pore complex. XZ view, it's sitting outside and inside the nuclear membrane, right? The resolution is 70 nanometer in the Z, optical raw data. Then we can also do a kind of tissue imaging. This is fixed mouse retina tissue, the synapse. We rotate in the X, Y, and Z to show the isotropic capability of our 3D stat, right? If you do it in the confocal, everybody has that experience. So you rotate Z, it's blurred out, right? Only to the X, Y, it's clear. Now from our system, X, Y, Z, it's isotropic, perfect. Then retina tissue is transparent. It's very thin. It's only like 40 micrometer. Then we want to do deep tissue multicolor 3D stat. We are the only one in the world who can do deep tissue multicolor 3D stat at optical, raw optical level without any post-processing. We use another adaptive optics. It's called ray shape. It's a commercial name, right? You shape all the rays in the microscope. The technical behind is deformable mirror. What's that? It's also space technology from the astrology. It's a mirror, but the surface can be tuned to compensate the light distortion. In the telescope, you use that to correct all the distortion of the beam. Here is the Uranus. Without a correction, the imaging resolution is poor. with that adaptive optics, deformable mirror, it's optical correction. There's no mathematical calculation. It's optical correction. You see a perfect image. We have exactly this one, but a small version in our microscope. And it can correct the optical distortion deep into the tissue. This is a cleared kidney sample from the surface deep to 80 micrometer. On the right side, we have the confocal imaging, we have the 3D STAD. If you see the 3D STAD, it's two-color 3D STAD compared to the confocal, the X, Y, and the Z resolution isotropically it's improved. And then with the deformable mirror, the shape is changed as the diagram showed you on the very right. You can image deep into H, which is 70 micrometer. On the left side, without this deformed mirror, it's dimmed deep into the tissue. Here's another example. Here's mouse brain tissue imaging, BRDU, to label the newly synthesized DNA, to study the proliferation of the neurons. Pseudo color indicated different Z layer. This example showed you human morula embryo. It's two-color imaging with 3D STAD and a ray shape for deep tissue imaging. Morula embryo human, it's 16 to 32 cells, this stage. Now we can imagine the whole embryo. And the ray shape can be applied also to confocal. This is a confocal imaging from us of the whole Drosophila larva. And then this is the zebrafish deep tissue imaging to see the neuronal projection from the dorsal to the ventral. And actually, these are my favorite example. It's coming from Taipei Academic Clinical. They imaging the whole Drosophila visual system, Z direction 123 micrometer of this sample. The orange neuron is a mutant. The Y-type neuron are blue neurons. They want to see the process of the orange neurons, how the process goes and connecting to the Y-type neurons. Without our system, previously they do the confocal and combine with the volume EM, then use a lot of computation power to find them together. Now with our 3D STAD, they do not need to do the complicated EM part. Directly with our 3D STAD, you can see clearly where the process goes. This example, they use our dyes for the best resolution. They use our 3D STAD. They use the flex exposure to protect the sample bleaching because you are doing a volume imaging, and then they use ray shape to correct the light distortion deep into the tissue. Actually, the institute, they are very happy. Actually, later everybody is trying to imaging and repeat their previous data with our 3D STAD MIRAVA. This is another example. Left side is the confocal. As I said, any STAD system, it's a perfect optical confocal system. So you see from the confocal, it's already perfect. But with the 3D STAD, the resolution is much improved isotropically. Then we have also the matrix APD array detector. It's an array detector. It's similar as Aeroscan. Everybody knows Aeroscan, right? Aeroscan is an array detector. However, Aeroscan uses PMT as the detection element. We use APD, very advanced detector. So it can also boost the resolution, similar as Aeroscan, via the post-processing to 70 nanometer. It can also reduce the background. And the computation power of this array detector is very strong. You can use this array detector to do film imaging. The commercial name is called time bone. Give time a color, rainbow, time bone. So actually, we're the only one who can do background-free, steady resolution level film. Okay, we are only doing very dim light, very few signal, because in the super resolution, you only see a very small volume, very fine structures. So the total photon volume is much reduced from those fine structures. So we are the only one who can detect that and do the film on that. And then based on this matrix array detector, we have our own deconvolution method. We call it TrueSharp. We deconvolve the image based on the background, based on the film of each pixel. The data, so actually it's not altering any, it's not artificial, I would say, because the normal conventional deconvolution method, you have to input theoretical numbers, right? What's the numerical aperture of the light? What's the diffraction index, and all these kind of things. We are doing the deconvolution on the imaging on its own. And with the matrix detector, you got already the background information and the film data of every pixel. So we can do a very good deconvolution. Actually, our TrueSharp is free of charge. You can even download it from our website to apply to any imaging method you have. Now let's see the performance of the matrix. This is the raw data of a patient. It's a gut biopsy. So it's raw data, it's a thick tissue, so the resolution is not good, the background is very high. Then we can use the matrix to boost the resolution, to remove the background, as you can see here. Then the matrix detector can be used to do the film imaging. We can do the film on a large scale. This is a Drosophila larva on a large scale, 3-color film imaging. We can also do it on a background-free, steady super resolution film imaging, 6 channels, as you can see here, right? Top 2 and the middle 2, the dyes from the spectrum point of view, they are very close to each other. You cannot separate them. While with the film time-bound solution, you can separate these 4. The lower 2 from the spectrum, you can separate them. So that's our film capability. Steady resolution film. And you can combine a lot of things together with this matrix detector. For example, this is the CaCO2 cell. It's an intestine cancer cell. So if you stain the actin, you see all the microcilia. The microcilia, they absorb the nutrients in the intestines, right? So if you stain actin. However, the confocal resolution is poor. You cannot see details. With our optical stat, the resolution is much improved. You can see how the microcilia, either they are lying down or they are pointing now to you, right? The structure, the resolution is increased, the structure is very well resolved. Then you can use the matrix to remove the background, to improve the contrast, the signal-noise ratio. And as I said, the matrix can calculate the fluorescence lifetime. Actually, you can do the post-processing to further improve the resolution. This is useful for those dyes which cannot handle a lot of stat power. So optically, you cannot reach the very high resolution. With the matrix detector, you can calculate the film time. Because in the donut, the film time is faster, while in the donut center, there's no steady beam, the film time is slower. It's normal, it's not slow, it's normal. So with this, you can do a kind of post-processing to mathematically improve the resolution. However, if you choose very good dyes, you do not need to do that. From the physical raw data, you can already get a very good resolution. So the last part is the mean flux. I will only give a very brief introduction because we are going to explain the mean flux on Thursday. So on the MIRAVA, we can do single color 2D mean flux imaging. While on the giant mean flux, you can do 2-color 3D imaging and tracking. Okay? So these are actually turnkey solution, actually. It's very easy to use. These are tested by the student. They are studying the ER. some molecules in the ER. On the left side is the optical raw data from the confocal. On the right side is exactly single molecule imaging of that molecule they are interested. And these are the students who's doing this experiment. So it's very, how to say, easy to use system and can achieve a very good resolution and very easy to handle. And then this is actually the last slide. So we have this system 3 weeks ago in East China at the Cell Biology Meeting conference. So on the left side, you see the system is in a conference room, okay, on conference floor. A lot of people are working here and here, there at the back. Even in that environment, we want to do single molecule imaging with the MinFlux module on the MIRAVA. In the middle, it's the working condition of our stabilization system. Please check, it's 0.3 nanometer. 3 angstrom in the XY and 9 angstrom in the Z to stabilize the whole system in a conference floor. On the right side, it's a customer sample. They bring a lot of samples. It's a PSD95 protein, post-synaptic density 95 protein. So actually that protein, it's a kind of a spring, right? It's a long and the short, and the diameter can change from 6 nanometer to 10-ish. The example we showed here, it's 7.18 nanometer full width half maximum. So this is to show you that even the MinFlux on a MIRAVA, it's so easy to use, and this whole system is not complicated. It's so stable, and we can even put it on a conference room. So this is actually the last slide. Actually, what you see here is the dual color imaging of the spectrin protein and adenosine, which is an actin capping protein. There's no structural details in confocal, while instead you see clearly periodic organization of these two proteins. And then further, you can do single molecule imaging of the spectrin protein, actually, in this example, with the MinFlux. That's all of my talk today. Thank you very much for your attention. I'm now open for questions. Any questions?
Hello, Xiaoyu. Thank you very much for the nice presentation. And I mean, it's gorgeous, to be honest. We really appreciate the MIRAVA. And I have actually was curious to find also application regarding extracellular vesicles and exosomes. And I'm wondering if you have other papers and also studies involving this matter. This is just because we observed very high growth of this field. And I saw some other also microscopy company that are pushing on this part. So I'm wondering if you have some other papers and application that you have made, the studies that involve labeling and also measurement for extracellular vesicles and exosomes.
Yeah. So I do not have a lot of published paper because this technology is kind of new, but I know a lot of our customers, they're sitting together with us to do the exosome things. And especially the labeling is very important. Because now you think, normally we use primary antibody, secondary antibody, the antibody size, 15 to 20 nanometer, 15 to 20 nanometer. The whole complex is 30 to 40 nanometer, right? The labeling complex, 30 to 40 nanometer. While our resolution of the MIRAVA is 20 to 30 nanometer. So actually you have to make the labeling complex even smaller. So actually we do a lot of workshop or training to our customers to design even this experiment with them. We have the nanobody to reduce the labeling error, to reduce the size. We even have labeling kit to put the dye directly to the primary antibody, or even to the antibody, even to the protein of interest. And then, as I told in the talk, then the customer has to know where he's going to label. So actually, we support several different exosome groups. They are doing a lot of research with our system. From the publication, I do not see yet. I'm very confident that it will come. Yeah.
Thank you.
Yeah, hello and welcome to our demonstration of our MIRAVA Polyscope. I'm not sure, one question, am I highlighted for all of you at the moment? Because normally we work with Teams. That works a little bit better with a screen sharing, but however, so am I nice and largely visible to everyone?
Yes, you look nice.
Yes.
Handsome.
Okay, very good. Oh, thank you very much, very much. No, it's just because yeah, I want to talk about our MIRAVA Polyscope, and I want to show you the system. So, well, give me 1 second. Oh. Should work. Sorry. There it is. But it seems the battery of the camera died, so I'm very sorry for that. However, you have seen the system. I'm sitting in front of it. Yeah, so we have like on the side the electronics rack where all the electronics is. Then the blue box you have seen is the optics box where all the magic happens, basically, where all the beam path is located, or our spectral detection units, and where the stat lasers are coupled into the beam path and so on. And we have it connected to an IX83 Olympus microscope, because we really like Olympus, because they have fantastic optics, so they have really top-notch objectives, and we are very, very happy with them. Anyways, why do we call the MIRAVA Polyscope? And this is because we can cover a wide range of resolution. So we can start with confocal resolution, then we have the matrix detector for background removal and also resolution increase in confocal mode. And besides that, we of course also have stat, and also our newest addition is MinFlux. As a MinFlux measurement lasts a few minutes, I will just show you how easy it is to work with the system. So we are also were able to make MinFlux imaging, as soon as you have a good sample, easily accessible. So I'm now sharing my screen. So can all of you see that?
Yes.
No complaints? Yes, yeah, okay, thank you. No complaints here, so yeah. Because a MinFlux measurement lasts a moment, so here's a measurement that I have previously acquired. You see our nice and famous nuclear pores, and I just want to give you an impression how easy it is to work with the light box and the MinFlux capability of the MIRAVA. But you will see that in greater detail with the MinFlux session on Thursday. However, the whole concept of the Lightbox is to make all the imaging capabilities easily accessible. So basically, all of the different modules, with just a few clicks, you get your image. And here I will just very quickly show you how to start a MinFlux measurement as soon as you have a well-defined sample. What we have here is U2OS cells with NUP96 GFP, and attached to that GFP we have a nanobody with a docking strand, and we have an imager strand in the imaging buffer. So it's in a DNA paint approach for MinFlux imaging, where we use the imager strand concentration in the buffer to create the blinking behavior which we need for MinFlux measurements. However, so I can start an overview here. Just adjust here the laser power for my GFP channel. I just go for live. And we are looking for the GFP to localize our regions of interest. And as you see here, so the whole stage is motorized. I can just by using the mouse wheel here focus. I can also move the stage around just by dragging and dropping. So, and then we see our nice nuclei here. We can just define a smaller region of interest here, in this case, the full nucleus, can again focus a bit. And then, so we have, from our bigger MinFlux machine, adapted our stabilization unit, of course, also for the MIRAVA. Because we are working in the single-digit nanometer resolution range, you want to have your sample as stable as possible. And for that, we have fiducial gold beads in our sample, and we look at the interference patterns of the reflection of the gold bead, because by doing this, we can stabilize our image in X, Y, and Z with a very, very high precision in the single-digit nanometer range. So I'm defining even a smaller ROI. I can go here for reference, so it looks at the image, looks at the gold beads, and takes a reference image so that it can see movements. So you also see here, so there is one moving gold bead. This is excluded. And as you see here, so we now have our stabilization unit locked, and in X and Y, it's below 1 nanometer precision, and in Z, it's roughly 1 nanometer. However, then I can basically go for my smaller ROI here, press start. See, okay, we are still nicely in focus. So, and then I can just go here to my MinFlux module. We have a blink check. I already mentioned we are using a DNA paint approach here to create the blinking behavior of our dye. So we have a blinking event always when the docking strand binds to an imager strand, and then it unbinds and the blinking event is over. But to check that, we have our blink check window here, so we can go for live. And what we are looking for is that we have nice and individual blinking events here across our ROI. And as this is a well-defined sample, I'm happy with what I'm seeing here. So I'm happy with this. I can then just go for the acquisition window here, define the excitation power, and start. And what we are seeing here is basically the detector frequency. So this is the APD detector, and this is basically what we are seeing at the moment is the dark noise. But always when we have this larger, broader peaks here, those ones, now the stabilization unit jumped off for reasons unknown. So let's do that again. Go here for live. Maybe let's take a new ROI, just like this. Activate our stabilization unit. Okay, but in general, you get an impression how easy it is to start a MinFlux measurement as soon as you have a well-defined sample. But because in the end, and here we see the first localizations appearing, and normally, so this measurement would take like 10 to 15 minutes until it's done. And we get our localizations here, as we see here. So this was one localization, a larger one where we could localize an individual fluorophore several times. However, as mentioned before, this is an image I acquired more or less half an hour ago. So you see that we have here our nice nuclear pores with the individual subunits of the nuclear pores. We could even go here, have our image with the confocal reference image here, could take it over here, and even overlay them. Second, change the color table to something that it's better visible. So we see that we have our nuclear pores here located in the nuclear pores of the confocal image. But here, of course, we have single-digit nanometer resolution, so we can see individual subunits of this nuclear pore, and we can measure with a localization precision of roughly 3 nanometers in a well-defined sample. But as I mentioned before, so all super resolution techniques come down to sample preparation. But the great advantage here with the DNA paint approach is that we are providing a kit where you get the nanobodies with the docking strand and the imaging buffer with the and the imager strands. And you can basically, each GFP cell line you have more or less directly transfer into a MinFlux sample by using our MinFlux DNA paint kit. Okay.
Bastian,
Yeah.
would you please do a line profile to measure the diameter of the nuclear pore complex and the distance between the subunit? Yeah.
Of course. So I could, for example, go here like this. Let's hit both and create a line profile. You're a little bit, and then we can just measure the distance here. In this case, it's roughly 190 nanometers, but this one is one of the bigger nuclear pores. So it's more an average, right? So could, for example, go here and measure those nuclear pores. And are in the range of roughly 100 nanometers in distance, diameter distance of the nuclear pores. Okay?
Yeah, thank you.
Also, one comment here. If you have questions, please interrupt me. I'm happy to answer all your possible questions. Now I would just change the sample to a stat sample. And there I will explain a little bit in a little bit more detail how the Lightbox software works and the imaging at the MIRAVA. Please give me a second. And as I said, if you have a question, please ask right away. Okay, I have to move around here a little bit. We can do it like this. Okay, so now I will define a new sample. Get rid of this and this. Keep this for later reference. And then I can define a new sample here. So again, I have a new sample with cells labeled for 5 different markers. So it's star red, star orange, star green, and star deep red, or CF680R, so a deep red dye. Then we can, of course, name our session. So this would be India remote demo. So of course you can name your session, give it a date, whatever, cells control or whatever you want to call it. You can name your different structures. So this is the Golgi. Here we have nuclear pores. Here we have nuclear pores again. And why we did this labeling, I will show you in a second. And here for reference, we have actin. And then you can also choose if you want to have, as long as each channel is individual, you can choose different color maps here. So what I do, as long as they're individual, the different channels, I just choose something that gives me a very good contrast. And then I can also choose overlay colors, which change the color map as soon as I overlay the different channels. Then I can go here, for example, something for colorblind people. And here we have our actin channel. However, and then in the Lightbox, everything starts with an overview. You always, by default, when you just recently have opened the software, it will start with 125 times 125 micrometers, which is one field of view for the 60x oil objective we are using here at the moment. But of course, you can change to any value you want, actually. But in general, we are working with overviews, which will be a tiling of different fields of view. And there we make a compromise between being decently fast and still have the image usable. So we're going with a somewhat larger pixel size, and then in the larger overview, we can start defining our regions of interest. So I can now go here for live mode, which gives a continuous image of the current field of view. Give it a second to wake up. Find the focal. I think I'm going in the wrong direction. There we are. So I'm just using the quartz focusing to find the rough focus, and now I can use the motorized stage and the piezo for focusing. So I'm just using the mouse wheel for focusing here. I can now adjust here the laser power in live mode, and then when I'm happy with that, you see we have our 4 channels here. I can press start, and it will now acquire an overview in which I can then later on define my regions of interest. So we give it a second. And as mentioned before, as long as these channels are individual, they give me something with a good contrast, but I have those little arrows here for overview. So I can just, for overlays. So I can just overlay the different channels by just clicking those little arrows. And have then my overlaid overview here. Give it a second to finish. So now we are done. And now I could basically just go here, define a smaller ROI, and I can also define 20 of those, mark all of them, and press play as soon as all the settings are adjusted. However, now I can, basically I'm deactivating this, speed the process a little bit up. Can go into my overview here. Again, focus a little bit maybe. So something like this. Now we have just a confocal image of our 3 channels here. We can overlay them. And just by adding, clicking on this little plus symbol here, we are activating stat for all of those channels. So I can then make a few adjustments here. For example, something like this. Let's say this should be enough. Maybe increase here the excitation for the stat channel a little bit. And then I press start. And get my first stat image. So, and if I wouldn't have done all the talking, like from putting your sample on to get your first stat images, this can be done in just a few minutes, right? So you just, as long as you know your sample well and you know what settings you probably would need, then it's super easy and straightforward to do your stat measurements. And as we see here on this panel our confocal channels, and here we see our stat channels. And now I can again choose my arrows here and do the overlay. And there we have our 3-color stat image with just a few clicks. Can also have side by side. So here we have the confocal and here the stat channel for comparison. Of course, it is not mandatory to acquire the confocal channel. You can just deactivate them if you're only interested in the stat images. That's totally fine. Of course, here in those demos, we always make the comparison. This is what confocal looks like, and this is how amazing your life can be when you do stat imaging, right? And then, of course, we have our processing here. So I could now go here and either drag and drop my different channels into that panel here. I can also go like this, and then we can go here for deconvolution. Adjust the settings here a little bit. Press run. And then we get a deconvolved image here of our STAT raw data. We always provide the detector raw data in the beginning, which is a conscious decision. We don't want to make an automatic deconvolution. We always provide you the detector raw data, and then we give you the opportunity to process your data further on. Also, when you have one of our systems, we have a free base version of the software, which can do all the things the software in itself can do, except controlling a microscope. And this software is for free. Everybody can have it. So everybody who has data generated with one of our microscopes can use the Lightbox for image processing, deconvolution, also image export, and so on. And just now, so here we have all the channels individual again, confocal, STAT, and STAT deconvolved. But then, of course, I can also do the total overlay. And now I show you why we have acquired or why we have labeled two different nuclear pore proteins here. So in confocal, you see, if we turn this off for now, you see in confocal, we have 100% co-localization, right? So each one is on top of each other. However, here with the STAT channel and also with the confocal, we see that, okay, our nuclear pore is forming rings. So this is a nuclear pore protein that is located in the periphery of the nuclear pore. And then we have the other protein here. This is something that sits more in the middle of the nuclear pore complex, right? So, and with that, we can nicely resolve this position here. We can get much more structural information on the nuclear pore proteins here and how they are located with respect to one another. I could now also, again, draw a line profile here, maybe this one, something like this. Create a line profile. And then we see that the nuclear pore protein that is labeled with star orange here is sitting perfectly in the center of the nuclear pore proteins that are located more in the periphery, right? And then we can again measure that and are again in the like 100 something nanometer range diameter of the peripheral nuclear pore proteins. Okay. Now, as you have heard today morning or in the previous session, that STAT imaging is power dependent. So meaning the higher laser power you use, the better your resolution gets. But of course, also the STAT laser are extremely powerful, and we also need to go over the sample several times to get enough photons for our further calculations for deconvolution. For example, so as mentioned, STAT is a very light intensive technique, and their bleaching might be a problem if you don't have stable dyes. If you're using star red and you are working with moderate STAT powers, bleaching is not too much of a problem as long as you acquire single frames. However, I'm now defining a new ROI, something like this. I'm only going for one channel now. So again, we see our nice nuclear pores here. But now I'm defining a smaller ROI just in this area here. And now I'm activating STAT and go for 80% STAT power. Even a little bit more excitation here and a few more line accumulations. Press start. And again, we see our nice nuclear pore rings here. And as you see, as we are working with smaller pixels, it lasts a little bit longer, and we put quite a bit of laser power on our sample here. So, and now I can go for the deconvolution again. And now we see with this high STAT power, we can actually start seeing individual subunits here of the nuclear pores. Right here, here, for, yeah. Let's get rid of this. But now, as I mentioned, STAT is a light-intensive technique. So if we now acquire this image again, we see, oh, okay, we bleached here a little bit, right? And then if you want to acquire more than one frame, this of course becomes a problem. So what I could do now, I can define this ROI here, and then now can just copy my previously defined settings. And we have our adaptive illumination schemes, or flexposure as we call it these days. So because let's face it, a fluorescent image is mostly black or background, right? So here in this area, there's no structure that we are really interested in, though we are only interested in our nuclear pores here. And we are at Abberior are extremely fast in switching our lasers on and off. So we can basically, in each individual pixel, decide if we want to turn on the STAT laser or not. So, and we can use this to measure the fluorescence in every pixel and then decide if it makes sense to do STAT imaging in this areas. Because only if we detect enough fluorescence, we know that there's a structure and it makes sense to do STAT imaging. This is extremely helpful for live cell imaging, where cells, for some reason, they don't really like to be illuminated with very, very high laser powers. Or on the other hand, if we want to acquire 3D volumes, so we don't want to pre-bleach the structures that are out of the focal plane, so we can also use it if we want to acquire nerve cells and brain sections, for example. Sorry. So now I can go here to our adaptive illumination schemes, can define here diamond one step, where we would just measure the confocal channel and decide based on this fluorescence where we want to turn on the STAT laser. But we can also do diamond two step. As I have mentioned, STAT is a power dependent technique. So the higher the STAT power, the better the resolution. But this is not a linear response. So it's negatively logarithmic, meaning that with 20% STAT power, you don't get 20% resolution increase. It's more like 20% STAT power is 70% resolution increase, and then the curve is flattening. And we can use this fact to refine our illumination mask even more. So I can now go like this and check if I'm still in focus. This looks good to me. I'm activating it again, just go for diamond two step here. Has remembered those settings. I'm even going with a little bit smaller pixels. And now I can press start. And now you see that the microscope is generating those masks here, right? So you see where this darker gray mask, where we don't turn on the STAT laser at all based on the fluorescence of the confocal channel. And then we see this brighter gray mask, where you refine our illumination mask by an intermediate low power STAT and can increase or like minimize the illumination we put on our sample quite significantly. Give it a second. Okay, now it's done. So I can go to my processing window here again, the deconvolution. And now we nicely see our nuclear pores, even to some extent with the individual subunits here. With the individual subunits here. Of course, that is not as good resolution as with MINFLUX, but it's already quite impressive, I would say. And if we now go back to our previous ROI here, press start again. And then you see that by applying this adaptive illumination schemes or flexposure module, we reduce the bleaching quite a bit. And in this area, I even use smaller pixels compared to that one. So we are going over the sample even slower, right? And by this, you can, as I said, for live cell imaging, dramatically increase the number of frames you are available you're able to image. Or, as I said, if you have more complex 3D volumes, this is also quite helpful to not pre-bleach structures that are above and below the focal plane. Okay. Any questions so far? Okay. One other extremely nice feature basically I'm the kind of the biggest fan of is that we can do 3D stat, but we can also do 2D stat, but we can also do 3D stat. So what we also can do, we can do a line ROI, and this is completely flexible. You can draw a line in every different angle. So our scanner is extremely flexible when it comes to that. So now I can basically go here, copy my settings again. So this is one of the basic concepts of the Lightbox, that you basically optimize your settings in 1 or 2 ROIs, and then you can copy those settings to all the following ones. So you could, for example, now go define 20 ROIs here, copy the settings over, and just press play and go. And let the microscope do the work. So again, I'm just going for one channel here because that's a little bit faster. So what I did now is basically I defined a line ROI, so it makes a section through our sample. I can press start. And what we have here is now 2D stat. As you have heard in the talk today morning, 2D stat gives you a resolution increase in X and Y, but not in the Z dimension, because we have the classical stat donut. But we have our little slider here, so we can now change from 2D to 3D stat by just going over to 100% 3D stat, press start. And now we did 3D stat of our nuclear pores here. Of course, we could also then again do a little bit of deconvolution here and get rid of the background and get a somewhat sharper image. And as mentioned before, so I could now, for example, go here, define a somewhat smaller ROI, copy my settings and deactivate stat for a second. I'm just going for live now. And I can now focus through my sample here, maybe something like this. And then we have our little dots here. I can just click on this, focus again, and do that again. Click on this dot, and now I have defined a volume, right? So you don't have to think what is up and below. You just press those little dots, and this way you can define the boundaries of the volume you're about to acquire. Now I'm activating stat again and press start. And as you see here in confocal, we are in theory already in the focal plane, but here more or less a little bit later, we start seeing our nuclear pores here, because the axial resolution of confocal imaging is so bad, or not bad, but roughly 600 nanometers. And here with 3D stat, we are roughly in the 100 nanometer range. So we get a much better resolution, and our structures start more or less later during our measurement. Well, we can then also have a look here in our volume viewer, where we can in real time see our measurement building up. And here for comparison, our 3D stat, which is kind of remarkable. So I have a tissue background. I did my postdoc in Drosophila developmental genetics, and I would have loved to have a microscope like this during my postdoc time. That would have made my life much, much, much easier. And now you can see, like, okay, those nuclei are quite flat, and in confocal you have you kind of see that there are 2 different layers of nuclear pores, but here you can nicely see the individual nuclear pores and see if you will look from the side and see here this nice taco shape of the nucleus or of this area. Then again, I can go here and do a deconvolution. Press run. Give it a second. Then, for example, I could change to a somewhat nicer color map. I like this one. This is basically my favorite, but this is up to your taste. And then you could, for example, also go here, export animation. For the desktop, in this case, export. And within a few seconds, I'm not sure if you can see this now. Can you see my desktop?
You are asking something, Bastian? Yeah.
No, just a question if you can see my desktop. Please give me a second. So I should be able to do it like this.
Yes.
Can you see that video?
Yes.
Yeah?
Yeah.
Okay. Very good. Anyways, and now you can see the software again?
Yes.
Okay, then I have to start sharing again. So, but now you should be able to see the software, right?
Yes. Yes.
Okay. Okay. Any questions so far to 2D stat, 3D stat, adaptive illumination? Or should we just do a Q&A in the end of the demo?
I think
I think
it's fine.
Yeah, you just go on. So if there's
Okay.
question, will pop up. Yeah.
Okay. Okay, as mentioned before, we can cover a wide range of resolutions. And we have another method for resolution increase. Normally we use stat for resolution increase. But if you have a very sensitive sample that is very prone to bleaching or can't handle stat illumination very well, you can also use our matrix detector for resolution increase. So you could, for example, then again, start a new ROI, maybe something like this. I again copy the settings over here. And just by clicking, we can activate our matrix detector. So the matrix detector is an array type detector, a little bit comparable to the Zeiss array scan, where we have an array of individual point detectors, and we can use the information of the light distribution over the detector array first to increase resolution, and also to reduce background in our sample. So this is what we mostly use it for, but you can also use it for confocal imaging to increase the resolution in the ZIM-like range, so roughly 100 nanometers in X and Y. So I can basically do this now, press start. We are still in 3D stat mode. Now it adjusts the spectral detection unit for the matrix detector because it sits in a certain position in the beam path. And now, so what you might have recognized that as soon as I activated the matrix detector, it puts the whole channel in a new frame step. So it would now first acquire this, and if those would have been active afterwards, it would have acquired this. And why we are doing this is so to get better results over for the matrix detector, we want to illuminate the whole detector array. So we completely open up the pinhole, so which gives you in the end a wide field-like resolution. But you might not want to have an open pinhole for your other channels, right? And for that, we have a little bit more background compared to the just 3D stat. However, we can now go to our processing again here. Can also apply our processing here for all the images we acquired. So this one, so we have our matrix here, do our matrix post-processing, and just press run. And we can use that to, give me a second. Yeah, okay. So now we got rid of the background here. So here we have a little bit more background, but with a matrix detector, we can measure which of the fluorescence is coming from the background and which of the fluorescence is coming from the actual focal plane based on the light distribution over the detector array. I can now go here. So I see I still have a little bit of background, so I can increase our differential detection value here. Press run again. And you see that you only get rid of the background without losing any information on the on your actual structures of interest. So it's not like background subtraction in ImageJ, for example, where you just blur the whole image and subtract it from the other one. So this here is based on an actual physical measurement. So we measure from where our photons come, and this way we can take it out of the equation. And as mentioned before, so we can also use that for confocal imaging and greatly increase our Z-sectioning and our resolution also in confocal mode. Although for resolution increase, we normally use STAT if you have a well-prepared sample, and then you can use the matrix to get rid of background where you might have a lot of structures in a tissue sample, for example. Then you can use the matrix to great effect and get rid of your background and only see the structures that are actually in the focal plane. So for comparison, like to see that for the whole thing, let's maybe do this. Copy the settings, deactivate for a second. So I can now focus here a bit. Not sure what this is. Let's take another one. Maybe this. So for example, something like this. Now I can activate 3D stat again. Let's start. And now you see that only those nuclear pores here are in the actual focal plane, and this is background fluorescence from structures that are above or below the actual focal plane. So what I could do now, I can again go to my processing window here and apply the matrix differential detection to my measurement and just get rid of the background. Could even increase the differential detection here a little bit. And only get rid of the background without losing information on my actual structure of interest. And this is also like the general impression I want to give you today. The whole operation of the Lightbox software and our microscopes is pretty straightforward and easy to use. So activating the matrix is just a click, and then you are ready to go and do your imaging. Okay. And with this, I would change to a new sample because our new module, the next module we want to cover is our time-bow module, which is fluorescence lifetime imaging, and time-bow is how we call it. So I'm changing the sample. And of course, there are more fancy applications for fluorescence lifetime, for example, like FlimFred and things like that. But to be honest, most people use fluorescence lifetime imaging for dye separation of spectrally identical dyes. So, so you can use lifetime information of dyes to increase the number of channels you might have in your sample. So I have changed the sample now to, again, cells where we have labeled the nuclear pores, as well as the Golgi apparatus. We can focus a bit. Here we have a dividing cell. And as you see here, so we have our nuclear pores and the Golgi with spectrally identical dyes. So you can play very long with a spectral detection unit. You won't be able to separate those dyes based on their spectral characteristics. So I'm defining a new overview now. And we see here, for example, in this cell, you see the nuclear pores and the Golgi here as well. So I could now define a new RI, go for live, and focus a little bit to be in perfect focus. And now I can just, by clicking here, this little symbol, this little checkbox, it's called time bow because this is what we call film imaging. And now we are basically telling the detector, okay, please measure the arrival times of each individual photon that arrives at the detector and sort it into individual time bins based on their arrival time. So I can now go here, maybe do a little bit more pixel dwell time, because the more photons we get, the better our calculations get in the end. So I can press now start. We see by this little symbol here that that we did lifetime measurement. So we have our little phasor symbol. We can now create a phasor plot where the different lifetimes are plotted around this half circle here. And so here are the shorter lifetimes and here are the longer lifetimes. And you see that we have this cloud of individual lifetimes in each pixel plotted on this phasor plot. And then we can just draw a line here, okay, and can separate our measurement into different channels based on their fluorescence lifetime. And this way we are able to separate individual structure from one another for spectrally identical dyes, but just based on their fluorescence lifetime, based on the arrival times of the individual photons that reach the detector. So, and this, of course, not only works for confocal imaging, but it can also define a smaller ROI here. Just activate stat and activate the lifetime measurement here for the stat channel. Press start again. And we get our like our confocal channel again. And now we did stat imaging here on the stat channel, lifetime imaging on the stat channel here again, indicated by our little phasor symbol here. Can again create a phasor plot to see our lifetime populations and can separate those into individual channels. Okay. But there's one downtime if you want to do lifetime imaging. Normally we do gated stat because the very early arriving photons are normally still confocal. So you need a little bit of time, or the stat laser needs a little bit of time to start working, or basically the fluorophores need a bit of time to respond to the stat laser. So the very first photons are still confocal. However, you can't use gating when you want to do film imaging, right? Because we want to collect all the available photons, as I mentioned, to improve our calculations for the phasor plot here. So we can't use gating, and for that reason, we have a little bit more background in our stat channel compared to a normal stat image. However, as we have heard before, we have a certain method to get rid of background. And this is another nice feature of our matrix detector. So the matrix detector can do time-correlated single photon counting on its own. So you don't need any third-party hardware. So at the moment, I did film imaging based on our APDs, where we have an additional film card here from PicoQuant. But in theory, as long as you're just interested in lifetime measurements for multiplexing, then you can also use the matrix detector for film imaging and also use the matrix to get rid of background based on the to get rid of background that is in your measurement because of the turned off gating. So I can again now copy my settings over here, activate the matrix, it jumps in another frame step again. We can increase the excitation a little bit, because also the matrix has a better time resolution and the longer linear response rate. Give it a second for the matrix detector to align itself. I can now focus a little bit, something like this. Now I can activate my matrix again. And what I could do now is I can now use this, do the matrix post-processing, get rid of the background, get a much nicer, much sharper image compared to the ungated stat image. And now I can create a phasor plot, see that even the resolution here in my phasor plot is even better, and now can separate the two lifetime populations into individual channels and have them in different channels, and got rid of the confocal contribution we have in our measurements. So that is quite nice, and as you have seen, also pretty straightforward to use. Right now I have my two individual channels here. One more comment here on lifetime. So also, so when you compare the phasor plot here to here, you see that the stat laser is also interfering with the lifetimes of the fluorophores. And this fact we can use to increase our resolution when we have, for example, very sensitive dyes. For example, green dyes like Alexa 488 or our star green are a little bit more sensitive to high power stat lasers. So you could, you can only work with very, very low stat power. But because the stat laser is interfering with the lifetime of the fluorophores, you can use the lifetime information to increase your resolution quite a bit. So I could also go here. Again, find a new ROI. Now I'm only looking at the nuclear pores here. I can do this. Focus a bit to get our nuclear pores. Activate stat again, but now I'm only doing 2% stat power. Start. We have still the lifetime analysis checked. I want to work with a little bit smaller pixel. Do that again. Now we have our lifetime information here. Can take this, and now we can do a phasor deconvolution, where we use where we feed the lifetime information into our deconvolution algorithm to greatly improve the resolution, although we only use 2% stat power. So the resolution increase compared to the confocal channel here in this case is minimal. So I could now go here, maybe make it a little bit sharper. We are not interested in intensity deconvolution, so I can now take this off. Of course, if you have a sample where you have more actual background, you can of course also include this in your deconvolution algorithm. However, now I can press run again, and as you see, we greatly increased the resolution, although we only used 2% stat power here. I think I could even go here a little bit higher. And improve it even more. And so here with 2% stat power, we still get a resolution of, well, maybe let's try this one. Create a line profile and make a Gaussian fit. And we get roughly in the 100 nanometer range resolution with just 2% of stat power, which is quite remarkable in my opinion. Okay. As mentioned before, so the MIRAVA Polyscope should be a sample for a microscope for all possible sample especially if you have something more complex like a tissue sample. So I will change my sample again, because so everybody who has worked with tissue and even in confocal imaging figured out that as soon as you go deeper in your sample, you will recognize that you're losing signal intensity and sharpness the deeper you go into your sample. And the reason for that is that, especially when we work with high magnification objectives, that you have spherical aberrations in your sample. So sample-induced aberrations which are induced by refractive index mismatches between your sample, your immersion medium, and the glass, and so on. So what I have here is, in this case, fluorescence beads in a 3D matrix, because there it's very nice to highlight what actually happens when you have spherical aberrations. So I'm doing this again, go for live. Focus a bit. And then you see that we have basically fluorescent beads here all over the place. And now again, I can basically draw a line ROI, something like this. And now I'm going for 100 micrometers imaging depth. So now here, 100 micrometers are covered. So I can now press start. Could even focus a little bit more deeper in my sample to have our fluorescent beads across our whole field of view here. A little bit more. And you pretty nicely see what happens with if spherical aberrations occur in your sample. So as long as you're close to the cover slip, everything looks very nice. We get nice PSFs here close to the cover slip. But the deeper you go, your image quality degrades significantly as in deeper sample areas. So for example, you could go here. We can now activate our adaptive optics module, or ray shape as we call it these days. It's just, again, one little click, and we have two sliders here. One is a correction value for the top of your sample. One is a correction value for the bottom of your sample, and it basically applies a gradient across the whole sample depth, a dynamic correction in each individual Z position, because the deformable mirror, which we use for aberration correction, is very fast and dynamic. And it's an electronic device, so it's also highly reproducible. So I more or less already know which values here work for my sample. So I can just activate that here, apply a gradient, and you immediately see that you get a much better image quality across the whole sample depth. And this, of course, is already extremely helpful for confocal imaging. I'll do that again. Okay, that's too much. This is already extremely helpful for confocal imaging, but 3D stat is particularly sensitive for spherical aberrations. And why is that? If you consider the original image here, was it that one? You see that the individual PSFs are smeared out in the Z dimension. And if you consider the 3D stat PSF, which consists, can you see that? Anyone? Can you see my little 3D stat PSF here? Yeah.
Yes.
Yeah, so what we have here, so this is the regular stat donut, but in 3D stat we also have light above and below. And if you now consider spherical aberrations, smearing that out in a Z dimension, so in the middle here there's an empty space, which is basically our intensity minimum. But if you smear that in the Z dimension, then you get your depletion light into your intensity minimum, meaning that you basically lose your stat signal completely. And this is why 3D stat is particularly sensitive for spherical aberrations. So you could now go here, we define a smaller ROI here in the bottom of our sample. It automatically adapts the correction values based on the Z position here in this area, can now activate stat again and go for 3D stat. Press start. And we get a nice 3D stat image in our deep in our sample here. Now for comparison, I'm just turning the adaptive optics module off. Do that again. And you see that you're getting close to nothing at all, right? If you compare those two, you see you don't get much signal anymore if you're in this deeper sample areas. And as I mentioned before, so this is a dynamic process, so I can just go here to our corrected value. I can now copy and paste the settings up here in my larger ROI here, which covers the whole 100 micrometers. Do that again. And you nicely see that we get very, very nice 3D stat PSFs here across the whole sample depth. And this is a dynamic process, as I mentioned before. So the deformable mirror, which we use for aberration correction, is basically correcting in each individual area of the image here in a dynamic fashion. And as I also mentioned, it's highly reproducible. So if you know your sample, so you already have a relatively good estimation what is a good starting value for your sample. And I now have switched off the correction again, and you see that the sample quality, the image quality degrades quite significantly if you go to deeper sample areas here. So I could now even go here, put them next to each other, and there you see that with a deformable mirror, you get very nice results across the whole sample depth, while without the correction, you only have a good image here in the upper part, and then the image quality is degrading. It's degrading a lot the deeper you go into your sample. And as mentioned before, so this is a dynamic process, and this is the beauty of it. So there are other means of to correct for spherical aberrations by adjusting the correction color, for example. But this you would have to do for each individual measurement. So you go to another position in your sample, you have to optimize your correction color settings, then you can do an imaging. You go to another area in your sample, you have to do the same again. But with a deformable mirror, it's as I said, an electronic device and highly reproducible. So you can just go here, define an ROI. In this case, I'm doing a symmetrical one here. I'm just copying my settings over here. It automatically knows the Z position, and I can just define an ROI, do a volume, and get very nice 3D stat results here. And then, of course, I could also consider this a larger overview. You go to another position in your sample, want to acquire a new ROI, maybe somewhere like here, but this time you are much, much deeper in your sample, right? You can go down here, even lower. And you see, when you have a look at this one, it directly corrects depending on your Z position here. So if I now press start again, you still see I get my 3D stat PSFs here. Could even turn that off. And turn it on again. So it's an electronic device. As I mentioned, it's highly reproducible. Yeah. Okay. And with this, I'm basically at the end. Are there questions? No questions?
I think maybe for a lot of people, it's the first time to see this system. and all
Yeah,
this-
sure.
They need time to digest.
Yeah, it's I mean, within 1 hour, it's quite a bit of information to process. Although I hope I could give the impression that everything is quite easy and straightforward. And
It
so
is
normally,
indeed.
yeah, normally I claim if somebody comes with a very specific task at hand, so like cells, and I want to acquire 3D stat volumes, then they give me 20 minutes, and then the person is able to work on its own. Only a beautiful thing about the Lightbox, you can't break anything, right?
Okay, then I think we do not have any questions, but yeah, in case anybody have any questions and if they drop us, we'll be sharing with you Dr. Bastian and Dr. Li.
Yeah, sure.
Okay.
Yeah. If you have a question, please write me an email, and I'm happy to answer.
Surely. Thank you so much, Dr. Li and Dr. Bastian.
Thank you. Thank you.
You're
for
very
attending.
welcome. My pleasure.
Thank you so much for the wonderful webinar.
Okay, then we close this
Okay.
session. I see you on
Yes.
Thursday for Influx.